Here we go. So today's topic is a very quick introduction to reinforcement learning. This is a topic that, of course, I can teach an entire course on, and we're not going to get into most of the details today. But I just want to give you a quick flavor of what reinforcement learning is all about. Some of you might choose to do your project on a reinforcement learning topic. As you know, we'll be doing projects this fall for the last part of this course. I'll share more details about the projects a little later, but I want you to have an introduction to reinforcement learning so that you can use it for your project or, to help prepare you to understand what it's all about. So in our previous lessons, we had this idea of a supervised machine learning model where we have some learner that interacts with the world. So it learns some model. It has some representation of some data that comes from the real world. In the case of supervised learning, this is a set of feature label pairs. And then given a new sample from the world, it can perform inference and predict the label for that sample. And we said that for any supervised learning problem, we'll have some loss function that we're trying to minimize. We have some training procedure. And then we evaluate the performance of the model by computing the loss for the new unseen data. Now, with reinforcement learning, that's very different. Okay. Well, let's actually summarize here. Okay, so we have some model y hat that's some f of x. We have samples up to xd. Okay. We minimize some loss function. Our training might be gradient descent on model parameters or something else. So we have this general procedure for supervised learning. Then for unsupervised learning, we had something slightly different. So here's an example of an unsupervised learning algorithm. This example was for PCA specifically, so let's learn to make it a little more generic. Okay, so we have some data representation that's just X. And the thing we want to learn is something about X. So it might be a cluster label, it might be reduced representation. And depending on what it is about X we want to learn, we might have different loss functions. For example, if we want to learn a different representation of X, we'll use reconstruction error. If we want to do clustering, we might use, let's say, the mean distance from each point to its nearest cluster center, and so on. So this was supervised learning, where we have feature label pairs. And then we had unsupervised learning where we just have feature data and we want to learn something about that feature data, like something about its structure. Now we're going to look at reinforcement learning. Reinforcement learning is a little bit different from both of these, and you can kind of think of it as being in between. Okay. So with reinforcement learning, we have some system F again. And the system F will interact with the world. So it will first observe, let's say, something about its state in the world. So it will observe its environment. So it gets some observations about its environment. We can represent those by saying it observes its state in the world. So where is it in the world? What is its context? Then the system will decide what it wants to do next in the world. So a reinforcement learning model is trying to learn something about how it should interact with the world. So the output of the reinforcement learning model will be some action. And let's say the system F is, we're now going to call it Not this. Okay, we're now going to call it a system pi. And instead of, let's say, learning some function of x, it's trying to learn some mapping from its observations of the world of its current state to some action A that it should take in the state. Now, when it does that, it gets new information from the world. It gets its new state, and it also gets information about the reward. So depending on what action it took, it might earn some reward. Let's look at a slightly different example. Okay, so suppose we have our little robot in this grid. So I'm going to draw a little grid here. Now, in this grid, this robot has a set of possible actions it can take. So let's say the set of actions is equal to let's just get some more symbols in here. So it can go right. It can go left. It can go up. And it can go down. So this is a set of possible actions it can take. Now, in this world, there are 8 states this agent can potentially be in. We call this little robot interactor an agent. Okay, so we have states S1, S2, S3, S4, so 8 states it can possibly be. All right. So the robot starts in some initial state. It has to decide where to go in this world. Now, let's suppose there is some sort of reward or penalty associated with either with different states or with taking certain actions in certain states. So for now, we'll associate the reward with a specific state. Okay, so let's suppose that if the robot reaches a state, then the robot earns this coin. All right, so what might the robot do to learn about interactions with its world? Well, let's say that for every time the robot does not earn a coin, okay, so let's say if the robot stays in place, it earns 0 reward. And if the robot moves, it earns -1 reward unless it reaches a state. Okay, so there's a penalty for actions of -1. There's a 0 reward and 0 penalty for staying in place. And there's a $100 reward for reaching this point. Okay, what is our overall goal? Is to maximize the reward. Okay, and we're going to say the reward is 0 for staying in place, -1 for moving, and 100 for reaching state S7. Okay. So we've introduced the idea of we have this agent. The agent is this robot learner here. and it's interacting with an environment. So this is an example of an environment it might interact with. It wants to achieve a goal in spite of some uncertainty about the environment. What is an uncertainty about the environment? Well, in this example, actually, everything we said was deterministic. But there may not necessarily be a deterministic environment. The environment itself might be stochastic. What do I mean? Well, it could be that when you reach this state, you reach some, let's see. Okay, so it could be the reward associated with a state is random. Okay, so instead of always earning $100 at this state, maybe sometimes you earn 50, sometimes you earn 100, sometimes you earn 150. So it might be stochastic. We also have state transitions, depending on the action. Now, in this case, we said, in this kind of toy example, everything is deterministic, which means if the robot decides its action is going to be to move right, then it always ends up in the next state, in the state to its right. But we could also define a stochastic state transition function, where if the robot decides to move right, well, with maybe 50% probability, the robot will actually move to the next state. But maybe there is also a 50% probability that the robot will encounter a wall and not be able to move. So maybe the robot is not always able to move. So the transition between states based on actions can be stochastic. So our reward can be stochastic. Our state transitions can be stochastic. And by the way, when I say the reward can be stochastic, any of this can be stochastic. So we might say for staying in place, the reward is 0 with probability 50% and 0.5 with probability 50%. So any of this can be stochastic. Now, those are things that are kind of inherent in the environment. So the reward can be stochastic. State transitions can be stochastic. And eventually, the learner is trying to learn some policy pi for moving from one state to the next. And that can also be stochastic. So that's what we mean when we say there is uncertainty. Okay. So it wants to achieve this goal of maximizing its reward, but it has some uncertainty about the environment. There's actually two kinds of uncertainty. There's an uncertainty because some of this is stochastic, and there's also uncertainty in that the robot just doesn't know much about the environment yet. Okay. So when we start off in this corner over here, we don't know what the reward is for moving to a different state. We don't know that there's a reward of $100 in step 7, in state 7. So at initialization, the agent doesn't know any of the following. It doesn't know a reward function. It also doesn't know the state transition function. So when we start off interacting with this world, we don't know anything about it. Also, a lot of the interactions we have with the world are stochastic. Okay, so we said the state of the agent at some time t is s. The agent chooses some action A. And let's say there is a discrete set of states in the environment and also a discrete set of actions it can take. And at each time step after taking an action, the agent earns a reward. And after that, the agent will observe its next state and take a new action. Okay. And the state transition function is probabilistic. So we can say the probability of reaching state S prime and earning reward R, given that we're currently in state S and took action A, is this probability. So the probability that the next state is S prime, that the reward is R, that our current state is, given that our current state is S and our current action is A. So this describes what we do, right? Our current state and our next action. And this describes what we observe from the environment. Okay, so we observe our next state and the reward from the environment. Okay. Now, over some time steps, let's say t time steps, the agent will take some sequence of actions and observe states and rewards. So it might observe a whole trajectory of interactions. So a trajectory of interactions might look something like this. You might say, I was in state 0, took action A0, got reward 0. Then I was in, you know what, I'm going to renumber these. I'm just going to call these, because I'm using S number as time steps. Okay, let's do this. Okay, so now this means the state, I was in some state at time 0, I took action 0, I received reward 0. Then I was in state 1 at time 1, took action 1, received reward 1, all the way up to state t. So we have some sequence of states, rewards, actions. We can think of this as a trajectory. Now, given some trajectory, so we have this information, what are all the things that an agent might try to learn? So what am I trying to actually learn in this situation? Any ideas? So what are some things I might try to be learning in this environment? In the case of supervised learning, it's very obvious what we're trying to learn. We're trying to earn labels. Very, very obvious what we're trying to learn. We're trying to learn labels. In the reinforcement learning case, what is it we're trying to learn? Okay, so one suggestion I see is how to take actions to gain reward. Okay, so one thing we might try to learn is this policy, which maps actions to reward. Right? Another thing we might be trying to learn is what are the objects in our environment? What is a state transition function? Right? So we might try to learn some model of the environment. What else might we want to try and learn? So we might want to learn something. So the suggestion is what not to do. That's included in the policy. So if we want to learn what to do, then we're also learning what not to do. But another thing we might try to learn is what are the consequences of different actions or different states in terms of their reward. So we might try to learn an explicit policy. So what action should we take in each state? We might try to learn something about the reward function, or what we might call the value function. So what kind of reward can we expect for ending up in a particular state or taking a particular action in a state? If we know all about the reward, then we automatically know the policy, right? Because if we know exactly what the expected reward is for every action or every state, then we can just pick the policy to maximize that. Or we might try to learn a model of the environment. Okay. Now, this kind of set of things we might learn gives us a taxonomy of reinforcement learning agents. So there are all different kinds of reinforcement learning models. So just as we learned a whole family of supervised learning models, there's a whole family of reinforcement learning models. And they're mostly organized by what they try to learn and what they don't try to learn. Okay. So on the one hand, we have, let's say, some policy-based models. A policy-based model will try to build an explicit representation of the policy. So we'll try to explicitly learn some mapping from states to actions. Then we might also have some value-based agents. a value-based agent tries to learn the value function. The value function is expected total future reward from a state. So that would be something like, let's say, learning that if I end up in state 6, I have some large expected possible future reward. What does the future reward of a state even tell us? Well, imagine we have some rule that if you get in state 4, you're just stuck there and can never move out. So suppose we have some policy, some environment in which once we reach state 4, no matter what action we take, we stay in state 4. Okay. What would be the expected total future reward from state 4 in that case? Okay. So we have these rewards. The reward is 0 for staying in place, -1 for moving, 100 for reaching 7. Suppose we somehow end up in state 4. What is the best action we can take? And my choice of actions are do nothing, move right, move left, go up, or go down. So my robot's in state 4. We said that once you're in state 4, you're stuck there. If the robot tries to move, it will earn, if the robot does nothing, it will earn 0 reward. If it tries to move right, it will earn -1 reward, but it will stay in state 4. If it tries to move down, it will earn -1 reward, but also stay in state 4. Okay. And same deal if it tries to move right or up. What's the best action it can possibly take? Okay. So go to 5 is not really an option. An option is move right, move left, move up, move down, or do nothing. Right? And we said that we have something about state 4 that once you end up in state 4, the state transition is the probability of reaching any other state given you're in state 4 and take any action is there. Okay, so we said we have some special state 4 that once you're in state 4, the probability of going to any other state, no matter what your action is 0, meaning you're always stuck in state 4. Okay, so once in state 4, your best possible action is to do nothing, right? You earn 0 reward for doing nothing. You earn a negative reward for trying to move. So your best possible action in state 4 is to do nothing. What is your total expected future reward from state 4? So we're going to call this the value of state 4. Okay. The value of state 4 is the total expected future reward for the state, which we're going to say is 0. Okay. So the best you can possibly get out of state 4 is 0 reward. Okay, so back to the taxonomy of reinforcement learning agents. So we have some agents that are policy-based. They try to learn this mapping from states to actions explicitly. We have some agents that are value-based. So instead of explicitly learning a mapping from state to action, they try to learn the value function. So what is the expected total future reward for each state? Or they might try to learn the value of a state action pair. And then we have an implied policy, which is just select the action that maximizes that expected return. So we might try to explicitly learn a policy. We might try to explicitly learn a value function, and then you just have an implicit policy. You might actually do both. So there's a family of methods called actor-critic methods that try to learn both the value function and the policy. Then we also have categories of reinforcement learning agents depending on whether or not they try to learn a model of the environment. Okay. So we have some that are model-based. And with model-based reinforcement learning, we try to, well, we either know a model of the environment in advance, and then we can, let's say, plan ahead. And instead of taking action at a specific time, we can try and use a model to predict future states. What do I mean by that? Well, suppose this agent has a model of the environment. Okay. So instead of directly taking action, it can use a model to perform computations, and it will know what the result will be of different actions. I'm just going to move this over. Okay, so suppose I had a model of this environment. Okay. What might I do? Well, I might do a little search, right? And I can do, depending on the state space, I could potentially do a complete search of the environment. So I might say, okay, given that I'm in state 1, I can perform computations on my modeled environment, find out that I can next move to state 2 or 5 or state 1. And for each of these, my reward is okay, 0 if I stay in 1, -2 if I move to, -1 if I move to 2, -1 if I move to 5. And then I could see where I might reach from those states. So then I might say, okay, from state 5, I could end up going back to 1, or I could end up going to 6. From state 2, I could end up staying in state 2, moving to 6, and so on. And I could, let's say, compute this entire tree in advance, and then sum up the reward I get all along the way. And then I could say, okay, I know exactly what sequence of actions I should take. So if I have access to a model, I can do some planning. And if I can do some planning, I could potentially do something better. Now, of course, we might not always have a model. We might not always be able to learn a model. But there's this whole category of reinforcement learning agents that are model-based. And then we have some that are model-free. So those that do not try to learn a model or that don't use a model, but that just interact with the environment by trial and error. Okay, so that's our categorization of reinforcement learning agents based on what it is they're trying to learn. Are they trying to learn a policy? Are they trying to learn a value function? Do they use a model, or are they trying to learn a model? And of course, we have some combinations of these. Okay, so given this agent interacting with the world, we know that like all machine learning problems, we're going to be trying to solve some sort of optimization. Okay. So we have some observations of the world, we take some action, we find out what our next reward is and our next state. Okay. And the variety of things we might want to learn could include the model of the world, it could include the policy pi, or it could include the value function. So let's try and formalize some of these. Okay. So we know that we get some reward for taking some action in each state. And we know that all of this can be stochastic, right? So we have some state transition function that tells us, given that we're in state S and we take action A, Okay, so take action S, A in state S. Then we have some probabilistic reward and some probabilistic state transition. So with some probability, the state transition function tells us what our next state is and what our reward is for that state action pair. So then we can express the reward function as the expected value of the reward in the next time step, given that we were in state S and took action A. And we can think of this as, let's say, just a probabilistic sum. So over all the possible state transition functions, we can think about what the reward is for each and then sum those all up. So we have some probabilistic reward function. Then we're looking for a policy, which is not necessarily just a mapping from state to action, but could also be a probability distribution. So instead of just saying, from state 1 go left, or from state 1 go right, we might say from state 1 go right with 25% probability or go down with 75% probability. So we have some policy that's a probability distribution over actions for a given state. And then we said we also have a value function. So let's call the return from some time t on g sub t. Okay, so this is the expected total reward from time t on. This is our expected cumulative future reward. So our future reward from time t on is our reward in the next timestamp, plus the reward in the following timestamp times some discount factor, and so on, until eventually we're summing all of our future discounted rewards. Why might we discount future rewards? So in our expected return, the reward for time steps in the near future is larger than the reward for time stamps in the far future. A few reasons. One is because we might have more uncertainty over in the far future. So we might want to prioritize that a little bit less. Another reason is because we just might care about current reward more. A third reason is just a practical reason. It's easier to do these computations if you know that the expected reward in the very far future can be approximated as 0. So we have some discount factor between 0 and 1. And then we compute the expected future reward function, or the expected future value function, as the expected return. Now we have two versions of the value function. We have one value function that's a v function. So given some policy pi, right, so the mapping of state to actions, we can say if we're in some state, the expected return for some policy, given that we're in that state, is v pi of s. So this is a state value. Back to our example here, we said that once we end up in this particular state, well, for the best possible policy, right? So suppose our policy is just always do nothing, then the value of that state is 0. For different policies, we might have a lower value. Now we can also think about the action values of a state. So the action value is a state action pair. So this says, given that you're in some state and you take some action, what is your expected return? So here, for example, we might say, given that we're in state 4 and we take action n, well, for the best possible policy, our expected reward is 0. What about if we take a different action? Let me just move this over. So suppose we're in state 4 and we take the action of trying to go down. What's the value of that? Okay, so we're interested in our current reward plus discounted future reward. Our current reward is going to be -1 for trying to go down. Our future reward, again, depends on the policy, but the best possible future reward we can get is 0. Okay. So for every state, we can define a value of that state. And we could think of it as, let's say, okay, so we're interested in the value given a policy. Depending on the policy, we might have different values. But we're mainly interested in what is the best possible value we could get, or what is the best possible state action value we can get. Okay. So in state 4 for action no-op, the best possible value we can get is 0. For any other action, the best possible value we can get is -1. Right. So this is the current reward plus the discounted future reward. And you could see that the discounted future reward is, let's say, some discounted version. Let me see if I can copy from this. No, I can't copy from this. Okay, so some discounted version of the value function. So we have, let's see, okay, we'll get to that. We can also think of a relationship between Q and V. Okay, so given some policy, we can sum the action values weighted by the probability of that action to get the value function. So what does that mean? Okay, so let's say I have a policy. That looks something like this. So my policy is from state 4, take n with probability 0.9, take down action with probability 0.1. Let's take a left option with probability 0.1. Okay. So we have some policy that says what to do in state 4. Okay. For that policy, let's think about what the value function of state 4 would be. Okay. So we know that value of state 4 is going to be equal to, all right, so the probability of taking action no-op, right, times Q of state 4 and no-op, plus the probability of taking action down plus the probability of taking action left. And let's say all other actions have 0 probability. So the value of the state can be defined for a given policy as the sum over the actions we could take in that state. We look at the sum of the probability of taking that action times the action value. Okay. Now, over here, we said that the action value of these different actions were, let's say for 4n, it was 0. For 4 down, it was -1. For 4 left, it was -1. But that's only true for a given policy, right? So this was for a policy of always n. Or let's say, so for a policy that says in state 4, you always do no-op, right? Then we had those defined value functions or action values. But now, when our probabilistic policy tells us sometimes you do no-op and sometimes you go down and sometimes you go left, we don't necessarily know what these Q values are anymore, right? So remember that the Q value is going to be the reward for the current action plus the expected discounted reward for the future. So we have something like this. So we know what the reward for the current action is in each of these cases. It's 0 plus something. So for each action we might possibly take in that state, we have our current reward, and then we have our expected future reward. Where this is going to be some discounted future reward. Okay. Now, what is V4? By the way, this is V4 only because when I take any action from state 4, I stay in state 4. So this value inside the value function is actually the next state. Okay. If I had a probabilistic state transition, so if from state 4, sometimes I stayed in state 4, sometimes I went to a different state, then I would need a whole bunch more sums over all those probabilities. So we can see that this is all very recursive, right? So I'm trying to estimate the value of state 4. Well, I can say that the value of state 4 is the probability of some action in state 4 times the value of that action, right? But the value of that action is itself defined using, let's say, the immediate reward plus some discounted version of the future value of the next state. So this is all very recursive. And how do we compute this? Well, okay, we'll get there. So we have our value functions. Now we have both a state value and we have an action value. So the state value is V, the action value is Q. We can also talk about the difference between them. This is what's called the action advantage A. Okay. So the action advantage tells us what is the relative benefit of doing certain actions in a state. So we can say what the benefit is of doing no op in state 4 versus doing go left in state 4. And given all that, we can say that the optimal value function is going to be the one that maximizes the return. So we'll call that V star. And we can think about the optimal value function in terms of the optimal state value function or the optimal action value function. Either of those will be the optimization we're trying to solve. And finally, our optimal policy is a policy that maximizes the value function. So we're looking for a policy such that the value we achieve by that policy, whether state value or action value, is equal to the optimal one we could achieve for any policy. So this is an optimization over all the possible policies. This is an optimization over, actually still over all the possible policies, where we're saying that we're looking for the specific policy that maximizes that value function. Okay. And we said we could also think of it as maximizing the current reward plus future discounted reward. So we're interested in the policy that maximizes the current reward for an action plus the discounted value of the next state. Why do we care about future rewards? So let's say we have this game. And suppose we try to play it using a greedy policy where we didn't care about future rewards. What would be the optimal policy if our discount factor was 0, meaning we only cared about current rewards? So if we only care about current rewards, well, if we're in the state, if we do nothing, we get 0 reward. If we do anything else, we get -1 reward. So if we discount future rewards completely, then our best action here is to do nothing. So we really need to consider the future because a long-sighted policy will often do much better than a very short-sighted policy that discounts future rewards very heavily. Okay, so given we're trying to learn this optimal policy, how do we go about learning it? So in reinforcement learning, what's the training data set? So the training set on which we train our model is not going to be the environment directly because we can't observe the environment. What can we observe about the environment? So the only thing we observe about the environment is samples of our interactions with the environment. And each interaction with the environment is, let's say we're in some state, we take some action, and we go to some new state and we get some reward. So this is our training data. We have samples of, given that we take some action in some state, we go to the next state with some probability, or well, we went to the next state and we earned some rewards. So this is an interesting challenge because the label, which is the action that we take in a given state, also affects our training data. So you can end up with all kinds of weird feedback loops over time where your actions determine what your model is trained on. So the output of the model determines the next input. So we have these training samples of, okay, given current state, I took some action, I went to the next state and got some reward. Let's imagine we do that for this particular game. So let's say we start off with a policy of always go left, always go right. What would this look like? Okay, so our samples would be, okay, we started in state 1, we went right. Let's say we have a deterministic state transition function where we always just move to the state we expect to move to. Okay, our next state is 2, and we earn reward -1. Okay. Next, we're in state 2, we move right. Our next state is 3, and we earn reward -1. Now we're in state 3, we move right, and we end up in state 4 with reward -1. Finally, we're in state 4, we move right, we end up in state 4 again, because that's our kind of like stuck state with reward -1. And then from then on, nothing changes. Okay, we can think of this as like a terminal state. State 4 is a terminal state. So the game ends if you end up in state 4 or if you end up in state 7 and earn the reward. All right, so I have all these training samples. How do I go about learning either a value function or a policy? Any ideas? Okay, so there's a suggestion. I can try and remember the state transitions and rewards at each step. Okay, so let's make a table. Okay, and let's say in this table, each row will be an action. So I have possible actions n, go right, go down. And then I have all these different states. Okay, so I have state 1, 2, 3, 4, 5, 6, 7, 8. Well, the suggestion was that I can try and learn I can try and remember the states and rewards at each step. Let's just try and remember the rewards. Okay. So let's say I remember that when I was in state 1, let's just do text. When I was in state 1 and I went right, I earned -1. And same deal when I was in state 2. So now I know this about my future rewards. What should I do next? Sorry, now I know this about the rewards. Okay. Well, I'm not necessarily going to be able to try every possibility. And remember, any of this could be stochastic. So it's possible that maybe I play a stochastic version of the game and I do the same thing and something else happens. But let's say we just try a different set of actions. So now let's say I start back at state 1 and I attempt the no-op action. And my new policy is always attempt no-op. So I just end up in state 1. All right, so now my table of instantaneous rewards looks something like this. Now suppose I end up in state 1 again. Right. Let's say I want to try out all the different possible actions from state 1. So I do that. And I find that if I attempt to go left from state 1, well, I stay in state 1 and earn action and earn reward -1. If I attempt to go up, same deal, I stay in state 1 and earn -1 reward. If I attempt to go down, I earn -1. Then I end up in 5, where if I attempt to go down again, I still keep earning -1. So now I know the instantaneous rewards with the policy of always pursue the same action. Okay. Now notice that for state 1, I have the entire column filled in. So I know the instantaneous reward of any action given that I'm in state 1. What should I do the next time I land at state 1? So currently this table tells me that the optimal policy if I'm in state 1 is to do nothing. But that's because it's only looking at the instantaneous rewards. So we don't only want to look at instantaneous rewards. We want to look at, let's say, the Q values. So the Q values tell us current reward plus discounted expected value of next state. So now we could say, okay, if we were in state 0 and we do no op, our Q value is going to be 0 plus V of state 0. Okay. Do you see the problem? So since everything is defined recursively, how do we go about keeping track of, let's say, all of our expected, let's say, of our expected reward or expected values? So one way to do this is what's known as iterative approximation. So let's say we start with some random values in this table. Now, we wouldn't start with all zeros normally, but let's say just for fun, I'll start with all zeros. Okay. So I'll start by observing a state. Let's just say there's a 0 in every cell here. I'm not going to actually fill them in. So we start by observing our state. I'm in state 0. And let's say I start by, I'm going to follow a policy where I choose the optimal action from each state. And if all actions have equal Q values, I'll randomly choose one with uniform probability. So I'm in state 1. Currently, my Q table says that the Q value for every action in state 1 is 0. So I'll choose from them with uniform probability. So let's say I decide to go left. Sorry, I'm going right. Okay. Now I'm going to observe my reward and my new state S. And I'm going to update the Q value here using my reward, which was 0, plus some discounted Q value for my new state. Okay. So my new state is state 2. Okay. And when I look at the discounted Q value for state 2, well, which Q value for state 2 should I use? Should I use state 2 and no op? This should go here. Should I use state 2 and go right, state 2 and go left? What should I do? So let's try everything, right? So I'm going to take a discounted value here. Let's find my gamma. Okay, I'm going to take gamma times the maximum value for any possible action I can take in the state. Okay. So let's say that from state 2, I could go left, right with let's say -1. Oh, sorry, they're all 0. So right now, all of my Q values have been initialized to 0. So I can go down with Q value 0. Up with Q value 0. Or I could stay in the state again with Q value 0. Okay. So what I'm doing here is looking for the max across all of these values in state 2. So I'm looking for gamma max of a bunch of zeros. So now my new Q value in state 1 is still 0. Okay, so far so good. All right, now I'm in state 2. Sorry for state 1. Okay, now I'm in state 2. I can make the same sequence of decisions. So from state 2, I'll end up in state 3. So within state 2, I end up in state 3. Now I'm going to compute, again, my Q value. Sorry, I forgot. I update this. So I need to update this based on my new reward. All right, so I updated the reward associated with going right in state 1 is -1, plus the max of all these zeros. That's -1. Now I'm in state 2. I chose to go right again, but again, randomly. So I have -1 plus, again, the max of all the Q values in my new state, which is again 0. Okay, now I'm in state 3. Let's say I take every action with uniform probability, but suppose I happen to pick the right one and I decide to go down from state 3. So what's my reward? My reward is going to be 100 plus, well, okay, it's still zeros. But anyways, this is a terminal state. Okay, so let's say my new reward is going to be 100. So I was in state 3. I went down. And my reward for going down from state 3 was 100. Okay, now I'm going to play the game again. Okay, let's play again. So I'm going to collect a new set of training samples. Now before, okay, so I play the game again, I end up in the top left state. Okay. What should I do from the top left state? So currently I have a 0 here. So I initialized everything in my table to 0. I have a -1 for going right. Now my current optimal policy will tell me never go right. That might not necessarily be good because we haven't really finished learning yet, right? So currently this is a very bad estimate of the Q value of going right because it doesn't include, let's say, this expected future value from here. So I might say that I still want to explore even suboptimal states. So let's say I'll decide that for a given state, with some probability, I'll pick an optimal value. And with some other probability, I'll pick a random value. This is called an epsilon greedy policy. So I want to trade off exploration, which is finding out about environment and finding out about rewards I haven't encountered yet, and exploitation. So take the action that maximizes the reward based on what you know about the environment. So I can use this epsilon greedy policy where with some probability epsilon, I choose a random policy, random action. Otherwise, I choose an optimal action. Okay, so I'm in state 1. Let's say I happen to choose going right again. Okay. Now, what's my expected reward for going right this time? Or let's say, how should I update the Q value this time? So this time I'm going to go right. My current reward is still -1. And my expected value of the next state is the max of -1 and all these zeros, so it's still -1. Okay, that stays the same. Now, suppose my epsilon greedy policy now allows me to go right again. When my epsilon greedy policy allows me to go right again, right? So remember, going right is not an optimal policy now, but I'm still exploring. So now my immediate reward is -1. And I'm going to add the max of, let's say, my value of the next state. So the next state is 3. What is the max value in the next state? So what's the max value in the 3 column? So the values in the 3 column are 0. Remember, I initialized all the empty cells to 0. So 0 for doing nothing, 0 for going right, 0 for going left, 0 for going up, and 100 for going down. So now my new Q value for, let's say, going right in state 2 will be minus 99. Okay, so let's, sorry, just positive 99. Okay, so my new Q value for going right in state 2 is now 99. So we can see that the reward from ending up in this positive state is starting to propagate backwards. Right? In each iteration, right, in the first iterations of this learning, I only learn about, let's say, my current reward. But in future iterations, as I repeat the process, I start to learn about future rewards because the rewards from the next state, right, will propagate back towards the previous state. So the first time I ran this, when I said, okay, go right in state 2, then as far as I knew, the value of state 3 was always 0. But now I know that there is an action in state 3 I can take that will give me reward 100. So this is actually greater. Now in this case, actually, I assumed gamma was 1. I didn't specify a gamma of 1. Let's say gamma is 0.8. Okay. So if gamma is 0.8, I have to discount this. So this is actually going to be 79, right? But that's still pretty good. Okay, so 79, all right, then let's say I take another action in state 2. Let's say I end up in state 3. I take some action in state 3. Let's say I take some action of going right. Okay. If I go right from state 3, my reward will be, my new Q value is -1, which is an instantaneous reward, plus the sum of all the rewards in state 4. All right, let's do another round. Oh, actually, no. We didn't finish this yet. I ended up in state 4. When I end up in state 4, I can take any action. So let's say I take the no-op action. And now my new Q value in state 4 is still 4, because I'm doing 4, plus discounted Q values from the next state, which is still 4. Now, let's say I decide to now go down from state 4. Okay, so now I'll fill in this. So the immediate reward for going down from state 4 is -1, plus the discounted best value here. Right. Now, let's say I decide to go down in state 4 again. What is going to be my new Q value in this box? Does it change? Okay, so I'm in state 4, I decide to go down. My immediate reward is -1. The best possible discounted future reward is 0.8 times the max of all these values. That's going to be 0.8 times 0. So we'll stay as -1. And no matter what I do in state 4, right, if I go up, I'll end up with a Q value of -1. So this will just fill in this entire column like this. Okay, let's go back to the beginning, play one more round. In state 1, I could take an optimal policy, which is do no op or go left or go up and go down. But let's say my epsilon greedy policy tells me this time, guess what? You're going right. Okay. Let's update the Q value for going right in state 1. So my immediate reward for going right in state 1 is -1. And now I need to compute the max of the entire column 2 and discount that. So I have max of 0, 79, 0, 0, 0. So now I have -1 plus, okay, let's say my discount factor is 0.8. Times 79. Okay, so it gives me a new Q value of 62. So now I can say that the expected value of going right in state 1 will be 62. So you can see that as you repeat this procedure, the future rewards start to be propagated back to earlier actions in the sequence. So I end up learning one sequence. So I end up learning a good sequence. Now, this approach is called Q-learning. It's one of only many possible approaches. Okay. And we said there's this whole taxonomy. Now, some of these approaches involve a sort of table like this, but some of them might involve models that are more similar to what we've seen before. So instead of filling in a table to try and remember Q values using a lookup table, we could try to learn a parameterized model. So we can, let's say, create a linear model or a neural network with weights. And then instead of saving values in a table, after we take some action and observe the expected reward, we can update the model parameters. So we'll look at this a little more on Thursday. I think that's all for now. Are there any questions?